talk at the DevOps Belgium. The video in English is already on YouTube if you want to look at it in English. Is there anybody who does not speak Italian? Can I switch to Italian? Ok, vabbè, yam. Italiano a modo mio, poi vabbè lo sapete come va a finire. Ok. Diciamo italiano, italiano di Bolzano Sud, ok. Ok, allora, vabbè, la maggior parte di voi credo che mi conosce, mi chiamo Mario Fusco, lavoro per Red Hat, lavoro Yes? Sorry? Should I switch back to English? Okay. We switch back to English. Okay, nice. Okay, my name is Mario Fusco. I work for Red Hat. I'm the project lead of Druce, the rule engine of Red Hat, and I collaborate to other projects in my company and also outside the company because, you know, it's open source. I'm here to speak about virtual threads in Java. Who knows what virtual threads are? Who is using it already? Okay. Last year I gave a first introductory talk about virtual thread. This is not that much introductory. I'm giving quite a lot for granted. I'm giving for granted that you know how they work and what they are, or I will have a small recap at the beginning, but mostly I wanted to bring my experience playing with virtual thread, the good part and the bad part of virtual threads. Okay, so just a very quick recap, as I said. So virtual thread, the main goal of virtual thread is to drop the one-to-one relationship between Java threads, between the native threads in Java and the thread provided by the operating system. So what happened before the introduction of virtual thread is that a Java thread was just a tiny wrapper around a thread provided by the operating system. This means that the thread was a scarce resource. It was costly to create a thread, and that's why we have thread pools. And it's a scarce resource. You can have just a few thousand of them, no more. Okay. If we drop this one-to-one relationship, meaning that you have a thread that is called the carrier, which is the native thread, and that the native thread can run multiple virtual threads by multiplexing them. So the idea is that the reason why you may want to have many threads is that some of those threads are not doing actual work. They do blocking operation. When they do blocking operation, since they are a scarce resource when you use native thread, you want to use asynchronous programming, not blocking programming, but that thing is very, let's say, the asynchronous code is very hard to understand, to read, to debug. It's impossible to read a stack trace because you don't have it at some point, or it's cut at some point. So you don't want to use the asynchronous programming, or you want the benefit of the asynchronous programming without paying the cost of readability. That's the thing. Okay, so this is why we introduced virtual thread, because we want to wait without paying the cost of freezing at a scarce resource like a native thread. So what virtual threads are really, really good for, in essence, is waiting without wasting a resource. That's the main point why virtual threads have been introduced. And then they are indeed lightweight threads. Okay, before, yeah, typically the metadata are 1/10 of a native thread. Typically, the metadata of a native thread are 2-3 kilos. Here we have 200 to 300 bytes. But this is not the main point. The main point why you are saving resources is that when you create a native thread, you are allocating 1 meg of space for each thread, regardless if you for the stack of the thread, regardless if you are using or not. Meaning that if that thread has a stack that is deep 2 calls or 2000 calls, you are paying 1 meg of memory regardless. Okay. For virtual thread, the stack is actually a data structure, a stack that is on the heap. So it's any other data structure in Java. So when the stack of your virtual thread shrinks, also that part of the heap is garbage collectible and reusable by other data structure. Okay, so it's not a fixed size like for native thread. Okay, and the other good thing of virtual thread is that for native thread, the context switch happens in the kernel space. For the virtual thread, it happens in the user space, meaning that typically is 10 times faster. Okay, so with all I said, it means, okay, virtual threads are great. Everybody wants to create virtual threads, and we are happy with them. So let's replace each and every native thread we have with virtual thread. Okay? And of course, this is not true. They are, so this is the main message of this talk. Next Monday, you don't go to work and start replacing each and every native thread with the virtual one, because there are pros and cons, and you know, it's one more tool, and you need to know, it's one more tool in your toolbox, and you need to know what they are good at and what are their limitations. And the main point of this talk is actually showing those limitations with practical example, based again on my experience. It's like 1 year that I'm playing with virtual thread, so I just wanted to bring my experience with this tool. First of all, virtual thread has a quite relevant problem with CPU-bound tasks. The most relevant problem is that they lack of fairness. They are not preemptive. When a virtual thread starts doing something, if it does a blocking operation, then is unmounted from the native thread, so another virtual thread can be mounted on that carrier and can do some other work. But if a virtual thread never performs a blocking operation, the virtual thread itself is not preemptive, so it will take the carrier and continue working forever until it's done, which is typically not something that you want. I mean, it's something that limit the fairness of your application. And of course, as I said, there is all this machinery to mount and unmount the virtual thread when they perform blocking operation, and the kind of signal that has to be sent to the kernel when this happens. All this stuff doesn't come for free. Of course, it has a cost that sometimes you don't want to pay. Okay. Well, there are other problems with virtual threads. One of the main problems is that nowadays still many libraries are not virtual thread friendly. Okay, meaning that if, for instance, if they perform a blocking operation inside a synchronized block, inside that synchronized block, the virtual thread is pinned to the native thread, meaning that if in that point it performs a blocking operation, you are not only blocking the virtual thread, but you are blocking also the carrier, which for sure is something that you don't want. Okay, so what we did, for instance, in Quarkus is that we had some synchronized block. We replaced all the synchronized block with the use of proper locks when necessary. We don't have many, but we have many locks around. We had a few synchronized blocks. We removed all of them because of this problem and replaced with proper locks. Many other libraries didn't do this step yet. They eventually will do it. But so far they are not ready to be used for virtual thread because of this problem. And another problem that um, found and I fixed in an important library is the use or sometimes misuse of ThreadLocal that doesn't work well with virtual thread, or in reality ThreadLocal work well with virtual thread, which is the problem. So, and I will try to show this with another practical example. And then the last problem is that, as I said, virtual threads are actually mounted on native thread, are mounted on a carrier thread that execute the virtual thread, and where the virtual thread performs the blocking operation, that the virtual thread is unmounted. So another virtual thread can be mounted on the same carrier. The problem is that this pool of native thread, which is the carrier, is typically dedicated fork join pool, and it's hard-coded in the virtual machine. It's not pluggable. You cannot decide, I want a different thread of pool configured in a different way to be used as the carrier thread. So, yeah, and this is a limitation. And by the way, we wanted to overcome this limitation and find the hard way why the limitation is there and why it's not a good idea to overcome it. Okay, so this is the topics. This will be the topics of my talk. The first problem that I mentioned is that the lack of preemptiveness. Okay, so what this means? It means that, as I said, a virtual thread will give the computation time to other thread, if and only if it performs a blocking operation. If it never blocks, it's not preemptive, so it will continue forever. And this has some implication, of course, on the fairness of your application if you are running a CPU-bound application that uses many threads. Let me show first example of this. So I have, can you read the code? Okay, so I have 8 cores on my machine, so this number it's returns 8 on my machine. So I have 8 by 8 64 executors, meaning that I have a code that is executed 64 times in parallel by 64 different threads. Okay, and the code that I'm executing in parallel is this one, which is very stupid code. Is just something that it's just something that keeps the CPU busy. It's a CPU-bound task that counts from 0 to 10,000 and does it using a big integer just to do some boxing and unboxing and creation of big integer instead of plain int, just to put more load on the CPU. That's all. It's a CPU-bound task. Okay, and I'm doing this thing, as I said, 64 times in parallel, and I can do this thing either using native thread or virtual thread. Okay, that's the thing. And then I run this 64 parallel CPU task, and I gather some stats about the execution. Okay, one last thing. To switch between virtual threads and native thread, I just do this. I pass the boolean to this thing that creates the runner. So this method returns the runnable where the CPU-bound task will be executed, which will be a virtual thread in case it's passed with true. Otherwise, it will be a native thread taken from an executor in case it's passed with false. That's how I'm switching between native and virtual threads. Okay, so let's run this once. I'm running this with I'm running this with native threads now that has preemptiveness. What happens now is that, okay, you have this 64 execution, and the duration is something between 1000, 1 second, 1.7 second to 3.4 second. Okay, then this is the average, which is a bit more than 3 seconds. And well, if you look at the number, they are, as expected, Gaussian distribution, more or less around this average, as expected, right? So all of these 64 threads take the CPU for a limited amount of time, has to share the 8 core, and at some point reach the end. Okay. Now let's do exactly the same exercise by switching this boolean. Okay. So now I'm doing exactly the same, but using virtual threads. And now you will see the effect of non-preemptiveness, okay? Now, the mean duration is much faster, you see? And the reason why is that when the first 8 threads start, they never leave the CPU. They continue till the end, okay? So you will see this 8 thread, and then you see this gap, of course, and then you'll see the second set of the other 8 thread, and then you see another gap. So you see there are 8 doing all the task till the end without never leaving the CPU, and then you have the other 8 and the other 8 till the end, okay? And so this is why the mean duration is so faster, because the first one who takes the first core was able to do this job till the end, okay? And in reality, if you look, the average is much better. Why? Because fairness is a cost. If you do context switch between native thread, the context switch has a cost, and you do this for fairness, which also has a cost. If you give up to fairness, the overall throughput, the average duration is better, but it's not fair, which is probably something that you don't want anyway on a CPU-bound task. Okay, feel free, of course, to interrupt me if you have any question about my example, if the code is not clear. Okay, as I said, another problem, especially with CPU-bound tasks, is that the scheduler has a cost. Okay, the mounting and unmounting virtual threads also has a cost. And I have another piece of code demonstrating this. This time I wrote a proper benchmark using JMH, and I'm running this benchmark with 100 parallel thread that could be virtual or native with the same switching policy that I showed in the former example. And this time, yeah, it's very similar to the example that I did before. I'm doing a CPU-bound task. The only thing, the only difference is that I didn't create a proper method that does a CPU-bound task, but I'm using this facility provided by JMH. This thing says just consume 100 cycle of clock, okay? So I have 100 threads, each of them consume 100 cycle of clock, and try to do this in parallel. And I'm running this benchmark with this parameter, meaning that the benchmark is run twice, one with the virtual thread and one with native. If I try to run this thing, okay, it's running very fast, so probably it's not super scientific, but you see a quite huge difference. If you run this with virtual thread, it takes typically the double of the time. It goes twice as slow than with native thread. Okay, why? Because now you have that cost of mounting and unmounting this virtual thread, and indeed I did some flame graph. Okay, yeah, if you was in the presentation of Simone before mine, you have seen some flame graph as well. As a flame graph is a visual way to figure out what's going on your CPU while running something, or what is taking your CPU. Okay, so the a bar is as large as much sample has been taken while sampling that stack. Okay, so the larger a bar, the most time has been spent there. Okay, but what we want in our case, in my benchmark, the actual work was done by, this is the actual work, right? So we want to maximize the time that the CPU is spending doing this work, which is the actual work. All other work is the thread coordination, which is a waste of time for this situation, for this benchmark. And if this is the situation with the native threads, so you see the actual work is done only in the 21, almost 22% of time. All the rest is the native thread quantity coordination. The problem is, if you do the same with virtual thread, now the actual work is that thing there, is like the 2%. All the rest is the virtual thread coordination. So this means that it needs to be done a lot more work to coordinate the virtual thread, and in reality, it has to be, this work is mainly done by those two things, the end and start of that notify JVMTI thing. That these are the 2 points where the Java virtual machine is notified that a virtual thread is mounted and unmounted from its carrier, and it takes time. Okay, so here in practice, I'm saying that okay, just a premise. This is a very extreme example. Okay, in reality, you don't have this situation. I'm pushing this problem to the extreme just to make it evident. Okay, but in this extreme example, when you do the work with the native thread, the 22% of the time can be used by doing some actual work, and with virtual thread, that time is only to 2%. Okay, so this is why it's much slower when running with virtual threads, and this is another problem using virtual thread in this case. Okay, yeah, okay, yeah, sorry, I put in evidence those two pieces that I was mentioning when the virtual thread is mounted and unmounted on its carrier. Okay, next topic is, this is also really interesting. It's about ThreadLocals. Okay, you know how ThreadLocals works in Java, right? Lots of people don't, it seems. Okay, what you can do with ThreadLocal is binding a variable to a specific, the value of that variable to a specific thread. Okay, so what I'm doing with this example is that I want to first determine the access right of a given user, and then I want to use the access right that for that user to perform an operation on a functional database. And what I'm doing here is that, okay, I discover if the right level of this request are admin or guest, and then I set the level of authorization inside this principal, which is the thread local, and then I don't need to pass that authorization level to the count to the bits. It's bound to the thread. The same thread is used to perform the operation on the database, so that value is retrieved from the thread local, and you know if you want to do which level of authorization you have for that request and if you can do it or not. Okay. And I'm putting this thing at work with virtual thread. I'm using virtual thread there, testing that code in the former slides. And if I run this twice, one with an authorized call and the other one with a non-authorized one, the expected result is that one of the two will fail because it's not authorized, and the other one will be served as expected. Okay, so we have this true thread performing this operation. One in the thread local asset is variable for an admin, so it can perform the operation. The other one in his thread local has set the authorization as a guess, so it cannot perform the operation and it fails as expected. So this means that with both native and virtual thread local work exactly in the same way, which is good, right? Which is what we expect. Okay, so everything is fine. What's the problem with thread local? The first problem is the number of threads that you have. Okay, as I said, typically with your application, you can have like a few thousand of native thread, but you can have literally millions of virtual thread. So if you have millions of virtual thread, it means that you have millions of variables on that thread local, and your memory footprint will be bigger and bigger. Okay, and then but there is another okay. There is a solution for this use case. The solution for this use case, which is still in preview in Java 21, I believe that probably will be a definitive feature of Java 22, is the use of scoped values. Scoped values works exactly the same way as the virtual thread, more or less. The main difference is that, okay, with scoped values, I'm binding a value to a thread, not a variable. Okay, so that the main difference is that this thing is immutable. That's the main difference. But what I'm saying here is that okay, I'm instead of binding the principal level to the principal thread local, I'm using the scoped variables, scoped values. Sorry, and when I run the thread, I set the right level of authorization on the scoped value. That this time again, as I said, is immutable, which is probably a good thing. And then I perform the call, and it works exactly as before. Okay, but you don't have this memory problem anymore because when the thread is done, and the value don't remain there. So the idea is that okay, that's nice. As I said, it will be probably feature ready in Java 22. And yeah, so the solution is okay. Let's just replace scoped variables, thread locals with scoped variables, which is unfortunately only part of the story, because this is the one that I showed you so far is the use case for which thread local has been designed, has been born. But historically, thread local have been used for another task, which is having a thread safe object pool. Okay, why? Because it's easy to use, easy to implement. You don't need to have an explicit life cycle for the resource that you are pulling on the thread pool, because the resource is there, only one thread can use it, so you don't have to take the resource and put it back. It's there, but only one thread can use it, so it's everything implicitly thread safe. Okay, but and scoped value doesn't work at all for this scenario. But this scenario works extremely bad with virtual thread. Let me give you another example with code, of course. So I have this task that is basically using a resource. So I have a task that needs to allocate a resource to be performed. And this resource is quite a huge array, so it's an expensive resource because it takes time to be allocated. So if you perform it 500 times, it means that you need to allocate that resource 500 times, one for each thread, okay? And if I run this thing, let's see how much time it takes. It should take around 12 seconds, if I remember correctly. 10 seconds and a half this time. Okay, good. So what I'm doing here is that I'm running 500 native threads in parallel. Each of them has to create this resource to serve the request. This resource is very expensive to be created. And in total, this benchmark takes 10 seconds and a half. Okay. So the idea is that, okay, but this native thread come from a pool. So what I can do is pulling that resource, pulling that resource on this resource pool, okay? So what I want to do is saying, okay, now use the pool. And what this implies is that if you use the pool, the resource is not created each and every time, but is taken from the pool, and the pool is this thread local. Okay, so in essence, I have 8 native thread because they are the native thread created from the executor. Remember, my machine is at core, so I'm not creating any more 500 resource, but I'm only create 8 resource that are in the thread local. So every time a native thread start, it takes the resource from the pool and use it. Okay. So if I run this by using this pool implemented with a thread local, just to be clear, this is a thread local. Okay. If I run this, it should take, you see, less than 1 second, 680 milliseconds instead of the second before. Why? Because I'm not creating that expensive resource anymore 500 times, but only 8 times. Okay? So the idea is that, okay, nice. Let's switch to virtual thread. The problem is when you switch to virtual thread, you don't have 8 threads taken from an executor. You have 500 virtual threads, because this is how our virtual threads work. Virtual threads are cheap. You never pull them. You always create a new thread, okay? So this means that, okay, now I have this thread local, but this thread local that is acting as a resource pool is totally useless now, because each virtual thread has its own slot on the thread pool. So you have to create 500 resources regardless. So you are back to the situation as before. Exactly that. So this is working extremely bad. Okay? In reality, what you want in this case is having a thread local that has key, not the virtual thread, but the carrier thread of that virtual thread. Okay? And you don't have it, or in reality you do, meaning that this is well hidden in the Java internals. There is this carrier thread local that does exactly what I say, but you cannot use it unless you don't do some tricks with reflection. But indeed, if you do, which is something you don't want, but if you do, I'm switching to that other carrier thread local implementation with still using virtual thread, and this is now fast again. But you don't want to do this, right? Because why you don't want to do this? Because that thing is as key not the virtual thread anymore, but the carrier thread. The problem is if the virtual threads does a blocking operation, it's unpinned from the carrier. Then it's when it restarts, is repinned, is mounted again, but it could be mounted on a different carrier. But then at that point, you have taken a resource from a different thread, not yours. And so it's not safe anymore. Okay, so you don't want to do this. And that's why it's internal. It's an internal thing of the JDK, but you are not supposed to use it. Okay, this is not a theoretical problem. It is a problem that is present in many libraries. This is the problem that was originally found by my colleague Francesco on Jackson and reported there. He opened the issue. We had a very long discussion with the Jackson maintainers, and at some point I got tired of the discussion and I provided a fix. So yeah, it's open source, you know. This is the spirit of open source. Okay, you not only open a bug and complain and please fix me, I need this. Okay, you send a pull request, and with some long time, you say that the conversation around this was 107 comments on this pull request. Of course, it was quite invasive. It was not really invasive because I was replacing the pool based on ThreadLocal with a different pool. The problem was again the life cycle, because in Jackson for this resource that is used, it's a huge array that is used to serialize and deserialize object in JSON. Okay, the problem of this resource is that it didn't have any life cycle at all, because if the resource is on a thread local, you don't need to say, okay, I'm done using this, I'm putting it back to the pool. So the problem of this pull request was not replacing a pool with another, is to create a proper life cycle for that resource, saying this is the moment when I'm taking the resource to the pool from the pool, and this is the moment when I don't need this resource anymore, and I put it back to the pool. Okay. So now in Jackson, with Jackson 2.16, 2.16.1 that was out like a few weeks ago, you have this new SPI where you can plug your own thread pool. Okay. The last problem that I mentioned is that you can, as I said, the virtual thread runs on a carrier, which is another pool of thread, of native thread. So virtual thread are mounted on a native thread, and the carrier thread pool is dedicated for join pool. That's all. Okay, so my machine has 8 core again, so I have a fork join pool made on 8 native thread, and those threads are the carrier thread for all the virtual thread that runs on my machine. Okay, and you are not allowed to change the pool of carrier thread, or better, you are not supposed to. Again, there is some internal trickery of the Java virtual machine that via reflection allows you to do so. So I wanted to try what happens if I replace it with other implementation of a pool. And yeah, what I found that the one thing in red is the native fork join pool. which is okay. I used the Game of Loom application that I used during my presentation last year, and yeah, whatever I tried, the original fork join pool is much faster than all other fancy implementation that I could imagine. Okay, so the question is, okay, so the fork join pool is good enough. Why you may want to replace it? The reason why we wanted to is because a very specific use case, well, very typical use case that we have in Quarkus. The fact is that if you think about it, the idea of virtual thread running on a carrier thread and the event loop that we have in Quarkus are exactly the same thing. Okay, what you do with an event loop is that, you know, on the event loop you never block, you don't do blocking operation, so you have a callback for blocking operation, and when that blocking operation terminates, you return from the carrier, from the callback, and you are mounted again on the event loop. Okay, and if you think about it, with virtual thread you do exactly the same thing, with the difference that you don't need a callback. You don't need to do fancy thing with nested function. You don't need to pollute your stack. It's much nicer to be read, but the machinery is exactly the same. Okay, instead of doing this in a callback, you do this in a virtual thread. When you do same thing as before, when you do a blocking operation with a virtual thread, the virtual thread is unmounted from the carrier, and when the blocking operation terminates, your virtual thread is mounted back to the carrier. So the carrier and the event loop are exactly the same thing under this point of view. Okay, so and in Quarkus we wanted to give you the possibility to run a specific task inside a virtual thread. So we have this experimental now annotation on Quarkus that is that at run on virtual thread. When you annotate a method with at run on virtual thread, means that the body of the method, that method is executed on a virtual thread. But when this happens, in reality, you have two thread switch that we may want to avoid. Okay, because the request comes to the event loop, then it has to be dispatched to the virtual thread, meaning that you have a switch between the carrier and the event loop, and when it terminates, you have a thread switch back. You have two thread switch that we may want to avoid. How we could avoid this? If we could plug the event loop of Quarkus as the carrier thread for virtual thread, it was exactly the same thread, so you don't have to switch from a thread to another when you execute stuff on a virtual thread. That was the idea. Okay? Is this clear? I'm losing you. Okay, in essence, we wanted to say, okay, I don't want anymore the native fork join pool to be the carrier thread. I want the event loop used by Quarkus to be plugged as the carrier thread. So the event loop and the carrier thread are the same thing, the same thread, and you don't have to switch from a thread to another, which are native threads, so it happens in kernel space. You don't have to jump from a thread to another and then back when running something on a virtual thread. That was the idea. Okay, I'm running out of time, but I'm not showing you the code, but in essence is that we try to do this and everything, and we end up with a deadlock, okay? We end up with a deadlock. Let me show you the code quickly. This code does exactly the same thing by using one single lock, and there are a native thread and a virtual thread trying to perform an operation that needs this lock. And the problem is that, yeah, I know. And the problem is that with this code, we have a deadlock with one single lock, which is totally counterintuitive, okay? How do you normally have a deadlock? You have a thread 1 which acquires a lock 1, you have a thread 2 which acquires a lock 2, and then the thread 1 needs the lock 2 to move forward, but the lock 2 is taken from the other thread, and the opposite. The thread 2 needs the lock 1, but it's taken. So you normally need 2 locks, at least 2 locks, to create a deadlock. The problem is that with this situation, we had a deadlock with one single lock, which was totally counterintuitive and drive us crazy to understand what was going on. Okay, and sorry I'm running out of time, but what was going on was in practice that the virtual thread was holding a lock, but couldn't run forward because also the carrier thread wanted to acquire the same lock, but it couldn't because the lock was taken from the virtual thread, and the virtual thread cannot move forward because his carrier thread could not move forward because it's locked. Okay, so this is the reason why you cannot plug your own pool. Okay, I'm done. The conclusions are clear. Know the tool you are using and use it properly. Okay, thank you.